Hello, in this video I'm going to talk a little bit about collecting and combining like terms. What is a like term in algebra? Well, they're basically terms that contain the same variables raised to the same power, right? Or as noted here, to be a common term, the term must have the same variable and exponent. The combining and collecting of like terms is quite a useful skill. It's a pretty practical, basic one, and one could argue maybe that it's perhaps quite foundational, in the sense that it's something that is very useful when you start dealing with much more complex algebraic expressions and when you start dealing with functions and things like that. The three steps really to keep in mind is the first step you want to do is you want to identify your like terms, okay? The second step is you want to organize those terms, and then you want to combine them. And once you get really good at this, you can do it really quickly in your head on the fly. But to kind of explain what those three steps entail, so first is identifying. So here we have an x term, right, 3x. We have another x term, so minus x. So I think those are the only two x terms, okay? Here we have a 2xy, so we have an xy term. We have a 3xy, so that's another xy term. Those are the only xy terms. And all we're left with now are two constants. Okay? So we have identified our like terms. Now we want to organize them. So we're going to rearrange this a bit, rewrite this expression. So we're going to write 3x minus x, right? Those are our two x terms, plus 2xy plus 3xy, our two xy terms, plus our two constants, plus 7, plus 9. And then the next step is to just basically combine these terms. So 3x minus x, well, that's just going to be 2x, right? Because if you have 3 x's, the pile of 3 x's, and you take away an x, you're just left with 2x. Here we have 2xy plus 3xy, that's just going to be 5xy. And then here we have 7 plus 9, and that's just going to be 16. And then we can simplify this. We can just write it as 2x plus 5xy plus 16. And that's it. Okay, let's do another one. Let's say we have 3 times a plus b squared minus 2 times 3a minus 4b squared. Okay, so this is a little bit different than the first one. And what we're going to want to do before we can identify, combine, and or organize and combine our like terms, is we're going to want to distribute this 3 like so, and this negative 2 like so. Now, in some places they teach the FOIL method. It's called FOIL, which stands for first, outside, inside, last. For instance, if you had a plus b times a plus b, first, so it'd be a times inside, outside, last, right? So it'd be a times a, which would be a squared, a times b, so it's plus ab. B times a is the same as a b, so it'd be plus ab, and then b times b is b squared, which you can simplify again to a squared plus 2ab plus b squared. Alright, that's the FOIL method. Personally, I like to think of it in terms of the more fundamental principle that's being practiced and employed, which is basically just the distributive property, right? Okay, the distributive property. All the distributive property states is that if you have a times b plus c, which you might notice is a similar pattern to what we have up here in this expression, right? If you have a times b plus c, such as this, what that equals is a b plus a c. That's all that the distributive property states, and so we're going to use this in this expression here before we can then identify our like terms. So 3 times a, that's just going to be 3a. 3 times b squared, that's going to be plus 3b squared. minus 2, now remember that's a minus, and negative 2, so 2 times 3 is 6, but it's negative, so it's going to be minus 6a, and then again we have this negative 2, and this 4 is also negative, so 2 times 4 is 8, but two negatives are positive, so it's going to be plus 8b squared. Now we can identify our like terms. We've got an a term here, we've got an a term here, it's highlighted in red. We've got a b term here, b squared term I should say, and we've got a b squared term here. It's highlighted in green, so we're just going to rearrange this to make it easier. So we got 3a minus 6a, those are our two a terms, plus 3b squared plus 8b squared. Okay, now we can just simplify and combine our terms. So 3 minus 6, that's just going to be negative 3a, and 3 plus 8 is 11, so that's just going to be 11b squared, and then what we end up is 11b squared minus 3a. You could write that the other way around, minus 3a plus 11b squared, but personally I prefer to have the positive out in front, just a little bit more neat and tidy. So we can do another one. Let's do one that's again a little bit different. Let's say we have we've got a 7 times 1 minus x squared plus 3 times 2 minus 3x plus 5x squared. And actually let's make this a 7x, okay? So that's 7x. So we're gonna, again, before we can identify and organize and combine our like terms, we've got to distribute. So we'll start with this 7x. Okay, so 7x times 1, that's just 7x. 7x times negative x squared, well, that's going to be minus x cubed. And if you don't understand what just happened there, in the future I can do a video on exponent properties, rules of indices, and things like that. So then for this 3, we're going to distribute, so that's going to be 3 times 2 is 6. Here, 3 times 3 is 9, but it's negative 3, right? We've got to remember. So it's going to be minus 9x. And then here it's 3 times 5, which is 15, so it's going to be 15 plus 15x squared. Now that we've distributed, we can identify our like terms, so just for the sake of clarification of what's happening here, I'll highlight them. We've got one x term, we've got two x terms, right, highlighted in red. We've got one x cubed term, looks like. We've got one x squared term, and we've got two constants, or we've got one constant, sorry, which I'll highlight in magenta. Okay, and so we can rewrite this as minus 7x cubed plus 15x squared plus 7x minus 9x plus 6, our lone constant. And now that we've reorganized this a little bit, we can combine our like terms. So there's no other x cubed terms here, just this minus 7x cubed, so that stays as it is. There's no other x squared terms, just 15x squared, so that can stay as it is. Minus 9 plus 7, that's minus 2, so this is going to be minus 2x, right? That there is minus 2x, and then we're just left with our constant. There's no other constants, that just stays as it is. And whoops, make that a little bit more neat, and we're done. Okay, and let's do one more. Let's do one that's looks a little bit more complicated. Just show you that really the process is the same. It's the same steps. If we have, for instance, 4m squared n plus 5mn squared minus 2m squared n plus mn squared minus 3mn squared. Okay? If you're not used to dealing with algebraic expressions, you might look at this and say, oh, okay, where does one start? But the key intuition, again, as we said at the top, is that to be a common term, the term must have the same variable and exponent, right? That's the key intuition here. So we go back down. So we're going to highlight, we've got 1m squared n term, okay, which is different than mn squared. So 1m squared n term, we've got another m squared n term, and that's all that we've got of those. And then we've got 1mn squared term, we've got another mn squared term, and we've got, one more mn squared term. So now we can we've identified our terms, we can combine. So that's going to be 4m squared n minus 2m squared n plus 5m n squared plus m n squared minus 3m n squared. Alright, so now we just, now that we've identified, we've organized, we can just combine. So 4 minus 2, that's just 2, so that's going to be 2m squared n. 5 plus, this is just a 1, okay, there's just a 1 right there, it's implicit, okay, so it's just going to be 5 plus 1 mn squared, which is going to be 6mn squared. And then if you take 6 and you subtract 3, well, that's going to leave you with 3, right? So then all of this equals 3mn squared. So we can rewrite this as 2m squared n plus 3mn squared. And that's it. We are done.